Hello, everyone. My name is Ziqi Li. I'm from Arizona State University. Hope you are all doing well and staying healthy at this time. Today, I'm going to present my paper for the SAM student competition. And my paper is primarily about a methodological development under the geographically weighted regression framework. And here are my co-authors and their affiliations. And I'll just get started. So GWR has been widely used in many domains, and it's a local modeling technique compared with a global model technique, such as the linear regression model. So GWR is to calibrate a local regression model at each location by borrowing the data from nearby, and while also applying a distance decay function. And such distance decay is controlled by a bandwidth which is a parameter. Well, actually, it's a hyperparameter that's used to control the spatial variation in the relationships. So by applying geographically weighted regression, we'll be able to capture the potential spatially varying relationships between the covariates and the response variable. So in GWR, there's just one single bandwidth used to control the spatial variation in the relationships. And there's a strong and a strict assumption that it seems that such spatial relationship or the spatial processes, they operate at the same spatial scale. So from the figure, you can see that they basically have the very similar spatial variation. And that's one assumption in GWR by using only one single bandwidth. However, a recent development by Foderingham et al. 2017 proposed a new method called multi-scale GWR, MGWR. So it's a very natural extension that is using covariate-specific bandwidth. So basically, it's using multiple bandwidths correspondingly for each spatial relationship between the y and the covariate x. So by using these covariate-specific bandwidths, MGWR allows the spatial relationship or the spatial processes to vary at different spatial scales. So, and then the bandwidths that we estimated from the MGWR model, they're indicators, they're very explicit indicators of how the spatial process operates over space. So for example, if there's a local process or localized relationship between covariate and the response variable, the optimal bandwidth will be small since the process changes quickly over distance. We need to use a small bandwidth kernel to reduce the any bias in the parameter estimate. And when the process changes slowly over distance, so this is like a regional process with some kind of spatial variation, the optimal bandwidth will be moderate. And when the process does not change over distance, so this is a constant process, there's no spatial variation, and you will get the optimal bandwidth to be very large and also possibly to be infinite. So the bandwidth selection in either geographic weighted regression for all the covariates or the multi-scale geographic weighted regression for each covariate is using a very commonly known concept is called bias and variance trade-off in model selection procedure. So basically, if you're using a large bandwidth than what it should be, you will introduce more bias, but because we include more points in the estimation, we reduce the bias variance. And this will give you a possibly under-fitting model. And on the other hand, you will be very likely using a small bandwidth, you might likely to get an overfitting model. So the optimal bandwidth should be able to balance the bias and variance. And it's a classic model selection problem. And the way of we doing this is to optimizing some penalized fit scores, such as IKIK information criterion, which is based on a information theory. So AIC, the formulation is here. So basically, there are two parts. The first is a negative log likelihood, and the second part, K, is the number of parameters in the model. So it's trying to balance out the fit and also penalizing not using too many parameters in the model. Or there's a corrected version of ASC, ASCC can also be used, or like Bayesian information criterion can also be used. So by evaluating ASC for each candidate bandwidth, we're able to select the best one, which gives us the most parsimonious model, and that's our goal. And this is a very general diagram that ASC will first drops as bandwidth increases, and then ASC will bounces up when bandwidth beyond the optimal. And we're trying to find the optimal bandwidth here. However, the selection of the bandwidth is subjective to uncertainty. So, and this is particularly very interesting and very important under the multi-scale geographically weighted regression framework, because we are getting a covariance specific bandwidth, like multiple bandwidths. And we're trying to use that to differentiate either local, regional, or global processes by comparing these optimal bandwidths. However, our bandwidths that are estimated are based on the data that we have, which is a single set of data, and it's not considering any kind of uncertainty for this data. So understanding these uncertainty for the bandwidth will be very important if we want to make inference about the bandwidth, and the bandwidth is an explicit indicator of the scale of how the spatial process operates. So by investigating the spatial process, we first of all try some simulation data. So we generated two surfaces. The first one is a little bit higher heterogeneity, and the second one with some lower heterogeneity. And we randomly draw some covariance and to reconstruct the Y. And we use this two data generating processes to investigate the bandwidth uncertainty. And a very intuitive choice will be through the bootstrap. The bootstrapping will be very useful in order to derive the distribution or the inference for a statistic when there's no analytical solution. In this case, following some literature, we use a non-parametric residual-based bootstrap method. So basically randomly resampling the residuals and then add it back to the fitted values and repeat that for like many times. And for each bootstrap sample, we calibrate a MGWR model and save the optimal bandwidth from MGWR. And we repeat that for 1,000 times so that we can get a general distribution for these covariance specific bandwidths. And here are the results. So we do this for GWR and also MGWR. So for GWR, the only single bandwidth that we get for these two processes is the green bars here. So this one, following a very kind of like a normal distribution. And in MGWR, we're able to differentiate this one single bandwidth into two bandwidths following two different distributions. So the blue bars is the bandwidth distribution that we get from the 1,000 bootstrap samples for the high heterogeneity process, this one. And for the low heterogeneity one, we get the bandwidth distribution following this one. And we are able to get 95% confidence interval by using the percentiles. And we can see that for the low heterogeneity process, we're getting a bandwidth that are significantly larger than the bandwidth for the low heterogeneity one. And what's most important thing is the bandwidth is subjective to the noise. So it's not deterministic. It should follow a distribution, is stochastic. However, using Bootstrap is computationally intensive because we need to calibrate at least 1,000 samples. However, we're trying to find another alternative, which is called IKIK weight. And it's a natural extension of ASC-based model selection by Burnham and Anderson in 1998. And it has been widely used across many scientific domains. And here is just a subset of papers that are well cited, using IKIK weights to understand the model selection uncertainty. And to use IKIK weight, we need to first define the comparison set of models. And here in this case, we're interested in a candidate of bandwidth from bandwidth 1 to bandwidth R, for example. And we calculate the minimum ASC from this R bandwidth. And for each bandwidth, we'll be able to calculate the delta of the difference between the ASC based on this bandwidth and the minimum ASC. And also we will be able to calculate the IKIK weight linked to that bandwidth K, WK. And the resulting IKIK weight is the likelihood of a given bandwidth being the optimal one. So for example, it has a very nice interpretation that a IKIK weight of 0.75 for bandwidth indicates that it has 75% possibility of being the best bandwidth that can approximate the underlying spatial process. And each weight, each IKIK weight ranges from 0 to 1, and sum of weights equal to 1. So these are very nice statistical properties that we can use. So to use IKIK weights to obtain the bandwidth uncertainty, also the bandwidth confidence interval, here's an example on how to do that. And this is the example for this high heterogeneity surface. So the optimal bandwidth that we get from MGWR for this process is 70. And the corresponding IKIK weight is 0.42. And how can we get the 95% confidence interval for the bandwidth is that we calculate the cumulative IKIK weight, and also when the cumulative probability achieves 95%, and then we stop. And then we include these bandwidths into the confidence interval. So basically that will include the 60, 70, 90, and 80 into the confidence interval. And also we can, similarly, we can get a 99% confidence interval if we include the 50 in this case, because the cumulative IKIK weight achieves 0.99. So a comparison of the bootstrap and the IKIK weights. So on the left-hand side, we have the bandwidth and their IKIK weights, and on the right-hand side, we have the bootstrap frequencies. So we can see that there's a strong degree of similarity between these two methods because they're actually measuring the same thing, which is the bandwidth uncertainty, although from different statistical approach. And from the 95% confidence interval, we can also see that for the process B1, it's quite similar, a little bit different from the process B2, but consider the bootstrap only uses 1,000 samples, it might not be very accurate, and also these two are two different methods. But we can see that using IKIK weights can measure the bandwidth uncertainty without doing so much computation. And what is more interesting is the use of IKIK weight can be used to derive the unconditional inference. So basically, it's accounting for the bandwidth selection uncertainty in our local parameter estimation. And this is following the multi-model inference approach of Burnham and Anderson, that we're averaging the models based on a spectrum of bandwidths with their according IKIK weights, not so that our model is not conditional on the single bandwidth, on the choice of bandwidth that we put beforehand. And we can average the local parameter estimates, and also we can average variance. So it has the inference here. It's kind of like a semi-Bayesian way of deriving the inference and also the parameter estimates for the MGWR. And we also do this for a empirical study, just to illustrate how can we use the IKIK weighted parameter estimates as well as IKIK weight derived confidence interval in the real case. So here we have a obesity modeling in Phoenix by using some demographic covariates. And here are the optimal bandwidths that we get from MGWR. And also we report the 95% confidence interval based on IKIK weights here. So we can see that for intercept and the percentage of annual checkup, people that doing percentage of annual checkup, their bandwidths are small and their confidence intervals are also small compared with the rest of these demographic variables, which means that the processes or the relationships associated with either the intercept or the percentage of checkup, they operate at a much localized level and is significantly localized compared with the rest of the variables here, because their confidence intervals are not overlapping. And also from the map, we can see here that the intercept and the checkup, they have very strong heterogeneity, while the rest of the variables, rest of the parameter estimates, they don't show a strong amount of heterogeneity. And and then so basically we can quantify, so these processes will be very local and these will be like regional and global. So concluding remarks is that we find that the bandwidth is subject to the random sampling variation that hasn't been investigated in the literature, and we find a way that we can use IK weight to quantify that uncertainty and obtain the bandwidth confidence interval. And this bandwidth confidence interval provide very important information for the uncertainty of the spatial process scale that's being measured. And we include this confidence interval in the two software, the MGWR 2.2 software, and also the MGWR Python package. So for one implication, what I think will be most important is in spatial statistics, we should be investigating the uncertainty of our spatial weight metrics, because in GWR, the bandwidth is actually controlling the spatial weight metrics. And however, in many of the spatial statistical models or spatial statistical measures, we only consider one specification of the spatial weight metrics. And this study basically helps us to understand how can we incorporate the different specification of those spatial weight metrics so that our results that are unconditional on the choice of the specification, and so that it will be more robust. So, so the reference, so this paper has published in the Annals of the American Association of Geographers, and here's the DOI if you want to see the details of the paper, because the time is quite limited in this presentation. And this work is supported by National Science Foundation, and I would like to thank you very much for your attention.